Environment Spatial Restitution for Remote Physical AR Collaboration, presented by Bruno Caby and co-written by Guillaume, Bataille, Florence, Danglade, and Jean-Rémy, Chardonnet. To provide some context, we began this work by interviewing network technicians about the potential uses of immersive collaborative tools in their work. The idea was to understand the constraints they face during their interventions. Technicians highlighted that they often can't instrument their working environments as they visit multiple different locations. For the same reasons, these environments can't be modeled or captured beforehand. Also, due to industrial safety needs and rules, video pass-through headsets can't be used most of the time. Based on their feedback, we decided to design a lightweight, real-time collaborative application that avoids prior environmental instrumentation and preliminary steps, to provide a flexible collaborative solution for technicians. We used optical see-through technology for all collaborators with HoloLens 2 to meet industrial safety rules and allow the remote expert to consult documentation or to update databases. Firstly, to reproduce an environment remotely in real time, we distinguish two categories. The first is video 360 degrees, which allows a vision with 3 degrees of freedom, as the remote collaborator can choose his own view orientation. This gives a better sense of freedom, although it is more difficult to understand the other person's point of view. So, we asked ourselves, can we allow more freedom in collaboration while maintaining a high level of mutual awareness? The second category is spatial restitution, which provides 6 degrees of freedom vision. Spatial restitution consists in rendering an environment with colored dots, or by reconstructing a mesh and texturing it. It allows remote users to navigate freely in a shared virtual space, and to communicate verbally and non-verbally with the local user. This method seems to offer more freedom and a space for interpersonal communication, but does it enable a high level of mutual awareness? During our bibliography, we identified a lack on fully dynamic spatial reconstructions works. Indeed, in most of them, a capture of the environment is performed beforehand, or the environment is instrumented with some sensors. Moreover, the remote user is mostly immersed in VR. However, we think that dynamic reconstructions and using optical see-through headsets for both users make collaborative applications more flexible and in line with technicians' needs. Motivated by these reasons, we designed a system using a dynamic spatial reconstruction of the environment, and augmented reality symmetrically. Our research question was, how does the use of a shared virtual space in which a physical environment is spatially rendered in real-time affect collaboration compared to video capture? Spatial restitution has some drawbacks. Volumetric reconstruction requires a lot of computation, and point cloud restitution demands a sufficient sensor resolution to display colored points and being able to distinguish objects. To use only the HoloLens 2 for sensing and computation, we decided to use the point cloud method and to represent the points by tiles whose size matches the sensor resolution, to project the environment texture onto them. We separated the different data streams. Verbal and nonverbal communication systems were managed by a photon server, and spatial and color data were processed and transmitted independently via UDP on different ports. This architecture allows us to update each part independently and without delay. A specific projection matrix for each frame ensures spatial correlation, and we consider the temporal offset small enough to neglect aberrations. Thus, we achieve relatively low latencies of hundreds of milliseconds by using only HoloLens for computation and wireless Wi-Fi connectivity. To evaluate our application, we designed a collaborative network assembly task, where the remote expert comes to indicate the assembly steps. The goal of this task is to connect a laptop to a remote router by using a fiber network panel. Although seemingly simple, the task requires precise gestures and the ability to render fine objects such as fiber optic cables. We used TeamViewer as a control condition. In this application, the remote user uses his laptop to see a first-person video of the technician's environment. He can talk to the technician and place 3D markers in his environment. In our results, we also distinguished the remote expert and the local technician role. To consider the remote user as an expert, we designed a cascading user study. For example, we consider that the red and the blue participants are performing the task, with the red one in the expert role. After the task, participants have to fill in forms. Then, the blue participant takes the role of expert to help the newcomer green participant, and the red participant leaves the experiment. This procedure allows us to consider the blue participant as an expert because he has already done the assembly in the technician role and has some diagrams to help him. We measured task completion time, mutual awareness, usability, and cognitive load. We also adapted Ho-E-T McDormand's Uncanny Valley questionnaire to qualify environments. Initially, this questionnaire consisted of 3 7-Likert scales corresponding to the 3 categories of attractiveness, humaness, and eeriness, with several scales proposed for each category. To adapt this questionnaire, we renamed the humanist category for realism and then selected the scales that best corresponded to our case from among those proposed in the original work. We made the following hypotheses. The empathetic aspect of collaboration will be accentuated in our condition. This is justified by the expectation that sharing a virtual space will lead to increased social presence, thereby facilitating interpersonal communication. We hypothesized that the environment rendering would be perceived as more uncanny in our condition. This stems from the idea that strangeness is tied to users' habits, which may be disrupted by spatial restitution. We postulated that task completion time would be shorter in the TeamViewer condition. This hypothesis is based on previous research that found no significant differences between solutions that render the entire environment, leading us to believe that partial environment rendering will be less effective. We expected cognitive load to be higher in our condition, especially for participants in the remote role. As suggested for H2, we think that rendering quality and user habits will favor the video solution. We found no significant difference in performance. However, our application resulted in reduced usability for the remote user, mainly due to the headset's field of view and the sensor aperture. All the 3 categories of the Uncanny Valley questionnaires showed clear differences in favor of the TeamViewer condition. Our application led to a higher cognitive load, especially for the remote user. It also enhanced mutual awareness, with the remote user better understanding his interlocutor's feelings. These findings allow us to validate H1. We also confirm H2 because the Uncanny Valley questionnaires showed clear differences between the 2 conditions, and these results align with prior works. Moreover, we did not find a significant difference in performance, so H3 was not validated, and we validated H4 according to the TLX's results. However, although performance was not affected, our participants indicated that the environment's restitution was far too partial to be usable. These results were observed on the usability scale and during the interviews. To conclude this presentation, we would like to highlight the key points of this work. We designed our application to comply with industrial maintenance needs in terms of flexibility, connectivity, and safety. Our cascading user study showed that sharing interpersonal spaces increases mutual awareness. Our participants also highlighted that OSTHMD needs to be improved in terms of optical field of view and sensors placement and aperture to enhance usability. Users' positions also had a significant impact on restitution's quality. Indeed, a good position is crucial for both local users, wearing the sensor, and remote users, who must find the optimal viewpoint. In this context, unconstrained incentives and nudges could provide a partial solution to this problem, while still keeping the experience engaging for users. In our study, we used a local Wi-Fi connection for transmitting data. Using more flexible connections as 5G and evaluate the resulting latency could lead to improved knowledge of the solution's usability in real-life conditions. Despite the discontinuation of the HoloLens program, our solution is usable with any headset providing access to its RGB and depth sensor. As new generations of XR headsets will integrate improved sensors, field of view and computing power, we think that usability will increase along with these improvements. Thank you for your attention.